So again, the title here is a mouthful. It shares much with many of the talks that we've seen this week in having a goal of understanding cognitive architectures better, but also more broadly, integrated systems and models of other sorts, and to some extent, all of AI and cognitive modeling. And it comes from a particular perspective of trying to analyze all this in terms of a framework for mapping the technological underpinnings behind all of this. So it shares with the common model an approach of abstracting, but abstracts even more than what we see in the common model. And it starts with dichotomies that abstract over the common model. So for example, from earlier work with a slight rewording, here's two different dichotomies that together classify three of the main components of the cognitive model, of the common model. You can see it for integrated systems and models, such as cognitive architectures. Here again is a slightly reworded analysis of the SOAR architecture, where we can see that in fact 4 of its major components, again, fit neatly into this 2x2 diagram. Again, but we're trying to also cover AI and cognitive modeling more broadly as well, but focused on what we can call just the core activities. So here that largely means memory processing and learning, not focusing directly on perceptual motor, natural language, et cetera, except to the extent that they're effectively grounded in the core activities. And the key question is sort of, how does analyzing all of this abstractly in terms of dichotomies tell us something useful about these various topics? So here's kind of where we start. You can view this as a table of the technological underpinnings involved in this particular work. There's a categorization at the left. It's kind of a non-orthogonal mishmash of categories. And then there's a set of modifiers or variants of these categories, which together produce many different kinds of technologies. Hopefully you can see many or all of your favorites here, but I'm not going to give you enough time to search for everything you want to find. The problem with this kind of categorization, of course, is it tells you very little about the technologies themselves. So in a sense, the goal of this talk is to progress from such a coarse and ad hoc categorization of technologies to n-dimensional maps that reflect their inherent structure underlying them. And then to use those maps to begin to scope out the technologies across AI and cognitive science, to understand them in terms of the structure of the space, similarities and differences among the technologies, trade-offs among them, and so on. And then to start to understand the rationales for integrations in cognitive architectures. For example, in the need to span trade-offs. So again, you'll see resonance from some of the earlier talks in this. The plan is to start by talking about general criteria that guide and evaluate work in AI and cognitive modeling and integrated systems and models, and use this as the basis for identifying trade-offs among them. Then introduce 4 dichotomies. So we got 4 dimensions here, but it's quite different from the 4 that, that Martin just talked about. The notion is that they jointly structure much of essentially the disciplines and systems and models. Not all of it, there may be other dichotomies, and there are aspects of some of the technologies that are completely captured by the dichotomies, but the idea is it captures much of the overall structure. We're then going to essentially map down many existing technologies down to these 4, essentially to get more unity, I guess you could say, in the field and to increase the power of these 4 particular ones. Then understand the trade-offs among the criteria they embody, overview how the cross-product of these 4 provide a way of looking at the full trade-off space among technologies, and then look at a few 2D, 3D, and 4D maps that come out of this. Certainly nowhere near the full space of such maps. And then very briefly exemplify kind of how to instantiate an approach to spanning the 4 dichotomies via the Sigma cognitive architecture, and in particular, how it's grounded in things that are shared with a common model and things that inherited from SOAR. Then I'll talk a little bit about a couple of particular things that were added in Sigma. Okay, so we're talking about criteria. We're talking about things that are relevant to guiding the development and evaluation of AI and cognitive modeling in general, cognitive architectures more particularly. They're often explicit or implicit within a discipline, but the goal is to make them explicit as possible here so that we can start understanding the trade-offs yielded by the dichotomies. The input for this is taken from a variety of sources, but you should still view this as very preliminary. What we're also going to look a lot at is the trade-offs implied by the dichotomies and how this often says that both poles have value rather than arguing about one versus the other side of them, as the field is often done. So here's the first group of criteria, starting with accuracy. And here I've got it divided up into 3 types. Whether you can prove you meet a standard, the degree to which the standard is met, or a minimal degree, or guaranteeing a minimal degree to which a standard is met. And those are labeled correctness, precision, and robustness. You could think of optimality as being a 4th perhaps, but that's not listed here. Efficiency, and the focus here is on time, both combinatoric, as we saw, for example, a lot in John Sotz's talk, and real time. There are also other forms of efficiency, but everything that's kind of faded out here is something that's not directly included in this work, but is included in these criteria slides for completeness. 3 kinds of generality in terms of the kinds of problems that you can attack, the kinds of capabilities that are included, and the kinds of entities that you model, and then a form of simplicity. So to some extent, you can see Andrews and Rick's talk focusing on forms of accuracy and efficiency to yield bounded optimality. But then they also have learnability, which we'll see on a later slide, in terms of deep RL. Martian's talk focuses on generality, I think problem generality and simplicity. It also has monstrosity, which I love that term. Sigma, the cognitive architecture I work on, has a desideratum of functional elegance. Now I can talk about that in terms of it being non-monstrous. So I'll have to think about that here, as well as whether optimality needs to be here explicitly. Here's the second group. So initializability, which we'll focus on in terms of learnability, which I've already mentioned. Usability, again, this is across AI and cognitive modeling. So some of these may be more important to certain efforts than to others, but usability in many efforts is important. And here we'll focus in particular on programmability, understandability, and explainability. And there are a whole bunch of operability criteria, which again are not the focus in this work. So there are 4 dichotomies we're going to talk about here. And the intent is, again, that they cover much of the field by mapping others down onto them. They will not, it's not intended to be, exhaustive, but hopefully it covers a large part of what we're talking about. So the first one I call asymmetric, and that's whether processing proceeds uniformly in all directions versus in a single direction. So a canonical example is logic versus rules. Logic, you can do deduction in all directions. In rules, forward is deductive, backwards is basically abductive. So although you can do inference in both directions, you get a different kind of inference depending on the direction that you do it. So that would be asymmetric. Inconsistent, whether processing considers a single consistent situation versus multiple inconsistent ones. So again, a canonical example here would be monotonic versus non-monotonic logic. Metadata, and this comes right out of the common model, whether the processing focuses on symbolic data versus numeric metadata. Although for the purpose of this talk, you can think largely of symbolic versus numeric. Here again, rules versus neural networks is kind of a canonical example. And the last one is non-combinatoric, whether processing complexity is exponential or greater versus sub-exponential. So here you have planning, which is clearly exponential in the general case, versus policies, which try to, in fact, have constant time processing. Now, these didn't just come out of thin air. So the first 2 actually came out of an earlier analysis that was looking at the structure of common model like cognitive architectures, plus a few other things. So here you see those 2 tables that we saw earlier. Based on these 2, with a relabeled y-axis. These three actually were used in an earlier analysis of essentially the coarse-grained dichotomy of symbolic versus subsymbolic, where in terms of the three dimensions that were used here, you could view symbolic as being symmetric combinatoric data and subsymbolic as being asymmetric non-combinatoric metadata. But beyond just these two extremes, you'll see there are a number of intermediate kinds of technologies, which is part of the power of this particular map methodology. You can also start to see interesting transition paths. So from logic, you can go to rules, from rules down to arithmetic circuits, and then from arithmetic circuits to feed-forward networks. Each of those crosses one dichotomy to get between those two extremes. As an alternative, you can go, say, from statistical relational AI to probabilistic graphical models to Boltzmann machines, which are almost equivalent, and then from there down to feed-forward networks. Again, one step in each path, and you get interesting kinds of approaches as you take each step between those two extremes. So here's our first dichotomy, asymmetric. Again, rules versus logic you've already seen, but heteroassociative versus autoassociative networks, feed-forward versus networks versus Boltzmann machines, for example. Procedural versus declarative memory is an example, and even attention networks versus self-attention networks, as we saw in Matt's first talk. But there's more. So for example, back propagation versus Hebbian learning, where back propagation flows in one direction in a backward direction. Hebbian learning is symmetric versus all the directions from you get input. And supervised versus unsupervised learning. And again, there's much more here. Sorry. So here's a first stab at looking at the trade-offs for this particular dichotomy across the set of criteria used here. The grayed out ones are ones that are not relevant, in this case, to this particular dichotomy. And what we're seeing here is essentially a trade-off between precision and combinatoric efficiency versus correctness and robustness. Again, won't go into details here. There's much more in the paper that I'm currently writing about this. But that's the rough notion of what you see in terms of the trade-offs here. Okay, let's go on to asymmetric. This is different ways that you can try to span this particular dichotomy. So one of the typical ones, and this leads to decreased elegance and simplicity, but it's a common way. So you add distinct modules for the two different poles. So for example, procedural and declarative modules, or shallow versus deep reasoning modules. Or in a way that's somewhat simpler and more elegant, you can directly try to support one pole in a way that can indirectly support the other. So for example, you can build autoencoders in feed-forward networks and declarative memory inside of procedural memory. Or in the other direction, you can do classification via generative learning, build some product networks out of graphical models by restricting message directions, and essentially build procedural memory inside of declarative memory as long as you provide an interpreter for it. Okay, the second dichotomy, inconsistent. We've seen one instance here. Another kind of standard one is fast versus slow thinking. There's, again, a bunch more here. One of them is actually backpropagation versus reinforcement learning. Backpropagation goes in a essentially consistent feed-forward network. Reinforcement works in an inconsistent sequence of stages. And if you span this network, you basically, this particular subdichotomy, you basically get D bar L. So that's one way of looking at what's going on there. You're trying to span consistent and inconsistent in such a way that you get both of the phenomena. Here, the trade-off can be looked at as basically real-time efficiency versus robustness, combinatoric efficiency, and problem generality. In terms of spanning, again, you can go with distinct modules. For example, reactive skills versus sequences and planners in 3T architectures, feed-forward neural networks, and monocolored tree search which is basically what AlphaZero combines, to get a consistent and an inconsistent component. Again, you can directly support one pole and indirectly the other. This is the technique that was called spatialization. In an earlier discussion, you had situation or step variables, and you can do that in logic and in graphical models and in neural networks to get essentially temporal models out of those, but spatialized. In the reverse direction, you can take, for example, a cognitive model, and you can take a monotonic system and promote it to inconsistency so that you can control it by doing a step of inference in each cycle and using knowledge to control it. Or you can take the cognitive cycle, which is inconsistent, but has a consistent subregion, which in Soren Sigma is called elaboration, and therefore get a consistent portion that's nested within an inconsistent mechanism. If we go back to our original 2D table and relabel the axes and abstract it a bit more, we get a table that looks something like this. One way to look at this is you can look at it as memory versus control with different forms of each. You can also look at it as an L-shaped representation of the 3 levels of control in a 3-tier architecture. Of course, then you can also flesh this out with all of these kinds of technologies. So it says that in a way you can instantiate a general kind of integrated system that has these 4 components in many different ways. Some of them will be simpler and more elegant than others. Some will have other kinds of trade-offs involved. But there's, in fact, a large space of possibilities, essentially for creating architectures that meet these 4 different components arranged in this fashion. Okay, the third dichotomy, metadata versus data. Just highlighted one other here. You can think of motor skills versus symbolic knowledge as an example of it, but again, there are other variants as well. Trade-offs here, it's simplest to think of this in terms of 2 trade-offs. There's precision versus correctness, and there's learnability versus usability as a way of understanding the trade-off here. If we're talking about spanning, again, distinct modules, you can in fact have modules for neural networks and rules. You can support metadata via data. For example, digital computers actually implement floating point calculations. That's really qualitative, quantitative, though there are slowness issues that happen when you do that in cognitive architectures. You can go the other direction and try to get, for example, symbols to emerge out of neural networks or implement logical operations versus tensor product representations. But there's a third path here, at least, which is you come up with a finer grained generalization or combination that subsumes both. So statistical relational AI does that with symbols and probabilities. Structured neural networks try to get relations as well as activations, and the common model in its metadata dyads does a form of this as well. Here's the abstract version of the 3D table. You can still see the basically 2D structure that we saw before, but here each of those original cells breaks into 3, including a spanning or hybrid row that we've added for those fine-grained interactions. Now, again, some of the things you can do here, if you go back to the coarse-grained subsymbolic versus symbolic, in terms of the 2 dimensions that are here, we get quantitative reaction versus qualitative reasoning. But if you add in the 3rd dimension here, you get a stronger contrast with qualitative reflection. You can, then if you shift that down 1, you essentially get AlphaZero, which span quantitative reaction with hybrid reflection. If you do hybrid versions of all 4, you get a form of the kind of thing you see in Soren Sigma and possibly other architectures as well. And then if you drop hybrid reflection, you get the common model because it does not yet cover reflection, but it does have data and metadata in all the other boxes. Again, this can be fleshed out in many different ways, leaving lots of potential flexibility in terms of building actual systems. Another kind of analysis you can do is look at the complexity, or if you want to call it the confusion about implicit versus explicit. You can see that mapped onto procedural versus declarative memory, fast versus slow processing, and subsymbolic versus symbolic representation in different works. But if you look at these three, the first one's really asymmetric, the second is inconsistent, and the third is metadata. So it's really three different dichotomies, all wrapped up in implicit versus explicit. So one way to think about this perhaps is that explicit is slow processing of symbolic declarative knowledge, or in terms here, inconsistent processing of symmetric data. And implicit isn't everything else. But there may also be more involved. So for example, there could be a long-term versus short-term memory issue involved here. There may be other things as well. Okay, quickly, the last dichotomy, non-combinatoric. An interesting one here is Monte Carlo tree search versus alpha beta search. They both are game tree search. The first one does a bounded number of paths though, so it's non-combinatoric. Alpha beta, though it does a lot of pruning, is still combinatoric. Again, trade-offs, there are two here worth note, basically efficiency versus accuracy, and simplicity and learnability versus usability. Spanning, again, just adding multiple modules. I'll kind of skip over that. Directly support one pole in terms of the other. So you can, for example, use universal planning to build a policy that covers all possible plans. You can build a memory that has all possible instances instead of storing generalized rules. In the other direction, this is the kind of thing John Sotzos was talking about. You can bound combinatoric problem space search in various ways. You can bound combinatoric analogy to get instance-based transfer and so on. Here's the first half of the 4D table that comes from putting all four together. I'm just going to comment on two things. One is that you'll see more consistent alternatives here than inconsistent ones. And you'll see a lot of bounded ones. Since these are non-combinatoric, those are all bounded versions of the corresponding combinatoric technologies. If we go to the combinatoric ones, it's actually much sparser, including at least one empty space where I couldn't figure out what goes in there. I'm not sure if this is a fundamental property, and if so, why that is, but it's an interesting thing to notice. Okay, if we go to Sigma, and its grounding in the cognitive common model and SOAR. When we're talking about asymmetric, one of the big new things in Sigma was to go with what are called extended graphical models, which can do things like Bayesian networks and factor graphs. But by restricting the directionality of message processing, we can support rules and feed forward neural networks as well. It also uses the restriction in SOAR where you can get deliberation out of reflection when there's sufficient knowledge to control the decision making. For inconsistent, we have two kinds of rules that differ in terms of whether they latch in working memory, again, as in SOAR, but Sigma adds on an open versus closed rule distinction there as well. You also get the knowledge versus problem space search distinction from SOAR, with the former nested within the latter. In terms of metadata, we've got these dyads from the common model, though here they're structured as lifted region tensors, which lets us deal with both discrete and continuous data, as well as probabilistic and activation-based metadata in a fairly simple and elegant fashion. Non-combinatoric, we have the notion of reaction or knowledge search and deliberation, which, assuming that knowledge search really is non-combinatoric or non-combinatoric versus reflection, all in a nested tri-level control structure for that. Related work, you can see the kinds of sources I went to look for criteria, for other work on individual dichotomies, for maps that are cross products of them, and for prior work that's tried to assess what's common among cognitive architectures. Okay, to summarize. So dichotomies partition AI, cognitive modeling, and cognitive architectures and other kinds of ISMs. Many of the key aspects can be distilled down to just four, though that does leave residuals that need to be looked at as well as the fact there could be other additional to just these four involved. Maps provide a more abstract level analysis than the common model. But in the trade-off, they give you a way of structuring and relating the space of AI and cognitive modeling approaches, and understanding the purpose and span of mechanism combinations in ISMs. In some sense, like what Andrew and Rick were trying to do, but in a broader, less elegant fashion, you could say. Criteria guide and evaluate work in AI cognitive modeling and cognitive architectures and help understand the trade-offs embodied by the dichotomies. And much clearly remains to be done. And hopefully I did it about right, and that's what I've got. Thank you.
Okay, a lot of good questions there. So we'll do a couple of them before we move on. So just as a sort of summary, like I've got this one from Richard, which is just that's some of the way I'm thinking of it. So basically what you're doing is this is a question, you're creating a space to kind of look at all the cognitive architectures, look at them, and you're kind of taking the criterion from the cognitive architectures rather than going from outside. That's what it is. That correct?
So the space covers more than just cognitive architectures. When you start combining cells or spanning dichotomies, you get into things that are integrated and like cognitive architecture. The individual cells are often individual technologies. The criteria were taken generally from computer science and AI, cognitive modeling and psychology, and from cognitive architectures as well. I've gone to, considered all of that. Now, they may be incomplete in various ways. I won't claim they contain all possible criteria from all of those disciplines, but the intent was to start from broadly AI and cognitive modeling, and even broader in some cases with computer science criteria and psychology criteria, and work our way down to cognitive architectures as being one particular way of looking at what this kind of a framework yields.